So this was our designs that we considered last time. So light passes through this polarizing filter. It's polarized. So this is a glass with electrodes. This is so-called twisted pneumatic liquid crystal. So, and this is the point that I want to go in details. This is multi-molecular layer system. Have a look. So this is one electrode, this is the second one, and this is a multi-layer that consists of the single monolayers, molecular layers. And this is, for instance, this is the single molecular. This is the second single molecular, and they are self-assembled like the spiral, you see, like this one. So if we don't have the electricity, the electrical potential in between these two electrodes, they are assembled as it is. However, when the electricity is switched, the location is different. You see, they are reconstructed into the perpendicular direction to the electrodes, just because of the properties of this molecule. So for the first case, for instance, this is a polarized light. It goes to the first molecule, excites this molecule, and this molecule re-radiate light, the same light as excites the molecule. So next, this light goes to the next one. And because this is a little bit twisted, so the radiation will be polarized in this direction. So the next in these directions. Finally, we have, you see, the circularly polarized light. So in this case, when we have the electrical potential, nothing of possibility to polarize light we have. So that is why the molecules are in perpendicular to the polarization direction of the light, and this light can't be repolarized and passes very freely through this filter. Is the idea clear? Ir skaidrs, lūdzu, jautājumi.
Ir skaidrs.
So, and as a result, have a look. We have here the circular polarization. Yeah, so now light is circularly polarized. And just this light, because of this filter polarization in the horizontal direction, the horizontally polarized light is able to pass through. Now, when it comes back, it's polarized again. And now this light is coming back. And we see light. When we don't have polarization on the filter, so we have this light in the vertical polarization. However, this filter cut off this light, and this light is unable to pass through. So that is why we have dark. And this darkness comes back. We don't have light, that is why we have the black digits here. So just some details about this. Tā, jautājumi, varbūt some questions? No jautājumu.
Pagaidām nav.
So now we go to continue. We have considered the membrane. We have considered the possibilities to transport ions. And we came to the situation when the ions pass the membrane because of the diffusion and the electrical current. Means we have the electrical voltage that assists transportation of the electrical charge. And plus diffusion, we have reached these equations. So, and finally, we have achieved such a formula that the diffusion coefficient is directly connected to the mobility of the electrical charge. So if the electrically charged particle, for instance, ion, goes through the membrane because of the voltage, so the particle has the mobility. But if the concentration of the particles behind the membrane and before the membrane, the concentrations are different, that is why the flow of the ions follows the diffusion mechanism. And in this case, in this combination case of diffusion and electrical transportation, the diffusion coefficient connects to the mobility. So this is the final formula that was achieved by Einstein. He worked both relative theory and some different things, a lot of different things. And one of the things is the connection of the diffusion with the mobility into the electrical field. So now this is our equation that describes the electrical current because of diffusion. I'm sorry, the flow of the electrically charged particles because of their diffusion and electrical transportation due to the electrical potential. So we know this formula from the previous lesson. So this is the diffusion element and this is the electrical transportation. So we know now how the diffusion connects to U, to the mobility. That is why we are writing the diffusion or mobility here. For instance, this is a mobility. We're writing this one here, and we have this result. So this is the total flow. And now we have that the total flow is directly proportional to the diffusion coefficient. And here we have the electrical potential gradient, and this is the concentration gradient. And there are constants. The electrical charge, the single electrical charge. So this is K, constant, T, temperature, and this is the concentration. So now, how the flow, the total flow, depends on these parameters that we have above. For instance, we have the constant of the electrical potential gradient, means this is the electrical field. The gradient of the electrical potential is the electrical field. Defeat the x, so this is the increment of the potential, and this is the increment of the coordinate. So this is the electrical field. So in this case, we can rewrite this formula by the following way. Divide with d, and here we have the same as above, but instead of this one, we have E, the electrical field. So on the other hand, we have the formula that describes the gradient of the concentration. So from this one, we are getting this one. So next, we can calculate the deepness of the concentration gradient. So have a look. This is a concentration and this is X, the deepness. And more deeper, less concentration, definitely so, because the diffusion process goes from the high concentration to the lower concentration. So that is why the concentration here is less than the concentration at the beginning of X. So now we can calculate the integral of this one. If you calculate the integral of this one, so this one is the result. We have changed minus here to plus and reallocate C0 and C. Yeah, now have from C to C0 instead of C0 to C. So, and from this one, we can calculate the deepness, how deep the particles are able to go in, to penetrate. So this is a formula of deepness. So there are limit of integrations, the limits of integration. And so just to get them here, we have such a formula. This one is here, and this is the exponent, and this one xkte can be written as the exponent because this is a natural logarithm. So to get this one, we have to calculate the exponent of this one. So we have it. So from this, we can get very simply the ratio of I total to the diffusion coefficient. And finally, the total flow. So this is a formula for the total flow. It's a complicated formula, but we know everything from this formula. So diffusion coefficient, single charge, electrical field, Boltzmann constant temperature. We know the concentration and we know the initial concentration. So we know everything to calculate the flow. Now we go to analyze the flow. Have a look. For instance, we have some medicine and we need to get this medicine into the patient organism. So let us increase the temperature. If we increase the temperature, so this one falls down, this one falls down. The exponent of this one falls down tremendously because if this falls down, this is the exponent, it falls down more significantly than this one. As a result, this one, if it falls down, the difference increases and actually very fast will come equal to unit. So this will go falls down to 0, and this and to altogether this will become 1 unit. So if so, because of the temperature, the diffusion coefficient increases too very significantly. We know this already. That is why the total current increases very significantly. So the questions here, please. So our conclusion from this long chain, increasing the temperature, we increase the diffusion coefficient and the total flow. So the questions, please. Lūdzu, jautājumi, vai viss ir skaidrs?
Ir skaidrs.
Now, what will happen if you increase the electrical field? So we increase the electrical field, we increase this one, we increase significantly this one, we increase significantly this one. Yeah, so this will increase, is increased. So if we assume that the current, the total flow must be positive, definitely. This means that this exponent must be positive, can't be negative. If it is negative, I'm sorry, yeah, can't be larger than unit. If it is larger than unit, we don't have this condition because it is minus here. So this one must be equal to unit, to more than 0. So, and this means that this can't be larger than unit. So in this case, if we increase this one, so means this one, from this, we have that the total current, total flow, this one, increases very strongly because of this exponent, and definitely because of this too. the question, please? O, vai viss ir skaidrs, lūdzu, jautājumi?
Kā to reāli var pielietot? Nu, ar temperatūru ir skaidrs, ja mēs varam paaugstināt temperatūru.
Jā, runājot par pacientu, jā.
Nu,
Nu, tad, ja mēs runāsim par pacientu par temperatūru, jā, mums vajag viņam palielināt temperatūru, nu, drusku viņu sakarsēt, jā. Viena no procedūram ir hipertermija. Runājot par elektrisko lauku, nu, tas nozīmē, ka vajag pielikt lielāku potenciālu starpību. Nu, vienīgi, ko nedrīkst viņu nošaut ar to, jā. Bet, nu, vajag piemeklēt lielāko elektrisko lauku. Es atbildēju uz jautājumu.
Jā, es vienkārši domāju, tas ir iekšā, tā kā starp,
Nē, drusku vēlāk pie pašas beigas mēs runāsim, cik liels vispār ir pieļaujamais elektriskais potenciāls, ar kuru droši var strādāt cilvēks. Tas ir saistīts ar šūnām. Tad, saprot, ja mēs pieslēgsim pacientam elektriskus potenciālus, tas nozīmē, ka visas šūnas atrodas elektriskajā laukā. Tas ir skaidrs?
Jā.
Un ar to es varu mainīt šo ārējo elektrisku potenciālu. Ja? Tad šūnam būs cits elektriskais lauks. Palielināšu potenciālu starpību, kuru pieslēdzu cilvēkam. Nu, tad šūnas arī atradīsies lielākajā elektriskajā laukā. Vēl es atbildēju?
Jā.
Vēl jautājumi, lūdzu. Please, questions. More questions. So the next one is osmotic phenomena or osmosis. So I need to switch the screen. Doesn't work. Why? I don't know. I need sound here. Nu, tagad ko. Tā viņš neieslēdzas. Es pārstartēšu. I'm going to restart because something is wrong. Doesn't recognize the speakers. Dzirdu mani? O,
Jā.
Jā, dzirdu.
Jā, esmu dzirdams.
okay, labi, paldies. So, osmosis. So let's assume that we have some vessel. And we have the membrane within the vessel. So this membrane here is semi-transparent. So this means that, for instance, from the left side, we have different particles, the large particles and the small particles. And this membrane is very transparent to the small particles. However, it is untransparent for the large particles. Now we have such a solution. For instance, on the left side, we have the mixture of the large and small, and on the right side, we have only the small particles. However, have a look. The concentration of the small particles here on the right side is higher than at the left side. So that is why the diffusion process will go on from right to left. So because of the higher concentration of the small particles at the right side. So we have the diffusion of the small. The same must be for the large particles. The concentration of the large particles here on the left is higher than on the right. However, the membrane doesn't allow to the large particles to go through. So that is why what we have, because of this process of the diffusion of the small particles from right to left, we increase the concentration of the small particles here on the left side. The large particle concentration is the same. So here we increase the concentration of the small particles because of these membrane semi-transparent properties. Vai tas ir skaidrs? Is this clear? Vai tas ir skaidrs? Lūdzu atbildiet.
Yeah.
So now let's try to predict what can be happen if the amount of the small particles here becomes less, and here the amount is larger. So this means that this part becomes lighter and this one heavier. In the case of the semi-transparent membrane, we can separate the masses. And now let's go to look at the video, at the movie.
What happens to a cell when it's placed in a hypotonic solution versus a hypertonic solution?
So the hypertonic solution means that the concentration of the small particle is less. In hypertonic solution, the concentration of the small particle is high.
A hypertonic solution is simply a solution that has a lower concentration of solutes, dissolved substances, compared to the inside environment of a cell. For example, water is considered a hypotonic solution since it is very low in solutes. A hypertonic solution is a solution that has a higher concentration of solutes compared to the cell's inside environment.
So salt
For
means
example,
the small
water
particles.
with a lot of salt is considered a hypertonic solution since it is very high in solutes. How can we examine the effects of a hypertonic solution on a cell? You might be thinking, well, I'm made out of 50 to 70 trillion cells.
So now let us assume that we mix this water with the cells. There is a high concentration of salt in this water, in this solution. However, the concentration of salt within the cell is less. However, the membrane of the salt is semi-transparent. The salt can't go through the cell membrane. However, the water molecules are able to go through the cell membrane. Next, the concentration of water molecule within the cell is higher, than here. So that is why we can predict that the membrane will be transparent for the water molecules that will go this way. Is the idea clear? Vai tas ir skaidrs? Alô? Alô? Jūs dzirdat mani? Allo, lūdzu atbildiet.
Jā, ir skaidrs.
Ir skaidrs. So when water leaves the cells, this is a dehydration of the human organism, and the organism may die. Have a look.
Drink this, I'll know what happens to cells in a hypertonic solution. But do not do that. Drinking salt water can be very dangerous as it severely dehydrates you. Nausea, vomiting, and even hallucinations are just a few symptoms of drinking massive amounts of salt water. Ask anyone who's been stranded at sea, which is unlikely because people who drink seawater eventually died due to kidney failure. So what you really need is a lab animal to conduct your test. Darn, she's too smart. Time to try her older brother. Well, that was a bad experiment. What's a better way to test how a cell reacts when placed in a hypertonic solution?
So next he was reanimated. So, but this is the example that really he could
Some
be
eggs,
killed.
like chicken eggs, are surrounded by a hard outer membrane which protects the semi-permeable inner membrane. This membrane is semi-permeable because it allows substances to leave and some substances to enter. In particular, the semi-permeable membrane allows water to both enter and leave the cell, but large molecules, like salt or sugar, are too big to pass through. The question is, how can we examine the semi-permeable qualities of this inner membrane with the hard eggshell in the way? Dissolve the outer shell by placing an egg in vinegar. Vinegar has a chemical called acetic acid. Eggshells contain calcium carbonate. When calcium carbonate in the eggshell comes in contact with acetic acid, a chemical reaction occurs. Calcium carbonate will break down to form carbon dioxide, water, and calcium acetate, thus dissolving the calcium carbonate shell. Within seconds, you'll see bubbles form. These bubbles are carbon dioxide that are produced when acetic acid breaks down the eggshell. Within 3 days, you should have a semi-permeable membrane free of the hard outer shell to conduct your experiment.
So after some days, the external shell of the egg was dissolved. So and now we have the membrane with the content inside, with the yellow inside, yeah, and the white inside. And now let's go to have a look.
Before starting our experiment, we will first mass our egg using a scale. Egg A has a mass of 94 grams. Egg B has a mass of 103 grams. Egg A we will place in a hypotonic solution, water. Egg B we'll place in a hypertonic solution, thick and sugary corn syrup.
So this means that for the hypertonic solution, we can expect that water from the inside part of the egg will go outside. So this means this egg must become lighter.
Egg A now has a mass of 97 grams. Egg A increased slightly to 103% of its original weight. We can conclude when a semi-permeable cell is in a hypotonic solution, water will enter the cell. Egg B now has a mass of 59 grams. Egg B decreased to 57% of its original weight. We can definitely conclude that when a cell is in a hypertonic solution, water will leave the cell. In fact, this is evident by the layer of water sitting on top of the corn syrup. However, 103% change in mass is not very significant. So how about we try this experiment again, but switch the eggs? This time, egg A is going in the hypertonic solution, which is still on the right. Egg B is going in the hypotonic solution, which is still on the left.
So we are changing them, replacing. So for the hypertonic, definitely water will come in, because in the previous experiment, this egg was located into the hypertonic solution.
After several hours,
and so
mash
the
your eggs
masses
again.
must be equal again.
Egg A went from 97 grams to 55 grams. Egg A has decreased to 57% of its original weight. Egg B went from 59 grams to a whopping 105 grams. Egg B has increased in weight to 177%. From this experiment, we can definitely conclude that when a cell is in a hypotonic solution, like water, water enters a cell. On the other hand, when a cell is in a hypertonic solution, like corn syrup, or more realistically salt water, water will leave the cell. Now that you're done with this experiment, time to play with those shellless eggs.
No! You're just gonna...
Okay, so thank you for this movie. So now have a look again what can be happen. When the small particles are traveling from right to left, the concentration or amount of these small particles here on the left side is higher. But the particles are moved because of the brown motion. So that is why these particles, the small particles, will increase the pressure in this left side. Is this clear? Vai tas ir skaidrs? Oh.
Yeah.
The pressure is increased. So that is why the level of the liquid here must rise up. And now we see the experiment that really demonstrates this phenomenon.
Bonjour à tous. Dans cette leçon, nous allons voir une démonstration sur l'osmose, dans le fond, comment les particules se comportent lors de l'osmose. Donc, pour ce faire, j'ai pris ici un bécher rempli d'eau pure à 100%, dans lequel j'ai mis un tube avec un liquide rouge. Bon, pour parler plus en détail du tube, ce tube-là est fait d'une membrane semi-perméable. Ça veut dire qu'elle laisse passer certaines substances, donc elle contrôle ce qui entre ou sort de cette membrane-là. Généralement, les trous qui composent la membrane ne peuvent pas laisser passer des grosses particules comme celles de sucre, par exemple. Donc, ça va seulement laisser passer les particules d'eau. Aussi, à l'intérieur, j'ai mis du sirop de maïs, qui est dans le fond de l'eau très, très, très sucrée. J'ai mis aussi un peu de colorant alimentaire pour que ce soit plus visuel, mais dans...
Shade, so this is a liquid with some small particle, higher concentration than inside, and this is a semi-transparent membrane. So these small particles will come here inside and increase, this particle will increase the pressure inside. As a result, this level must rise up.
L'exemple ici, ça n'a pas vraiment d'impact. Donc, si je plonge ce tube-là qui contient de l'eau très, très, très sucrée dans un bécher qui contient de l'eau pure à 100%. Donc, on a vu qu'au niveau de l'osmose, les particules d'eau vont toujours voyager de l'endroit où est-ce qu'elles sont le plus concentrées en eau vers l'endroit où elles sont le moins concentrées en eau. Donc, dans ce cas-ci, les particules sont supposées voyager du bécher vers le tube. Donc, ce qui fera en sorte qu'après un certain temps, le niveau de liquide dans le tube va monter, donc jusqu'à temps que les concentrations soient équilibrées. Donc, ce processus-là pourrait durer assez longtemps. Donc, je vous laisse l'observer pendant environ 1 minute. Vous allez voir que le niveau de liquide rouge va monter dans le tube, ce qui nous indique que l'eau est entrée à l'intérieur et que l'osmose a fonctionné.
Sugar, oh honey, honey, you are my candy girl, and you got me wanting you, honey, oh sugar, sugar, you are my candy girl, and you got me wanting you.
Okay, so thank you for this video too. Some questions? Vai visi ir skaidrs? Lūdzu, jautājumi. Ir jautājumi, lūdzu atbildēt.
Nav jautājumu.
Nav jautājumu. So now the question from my side: what can be done to prevent against this phenomenon, to prevent rising of this level? What can you offer as engineers, for instance? Hold on. Hello? Now you see the volumes doesn't matter. The level will rise again. Maybe not so significantly, but will rise. But I'm asking about to prevent, to break this process. Maybe more precisely is to ask to break the process, to stop it. What can be done? How? To go to the 0 Kelvin? No idea. But so just mechanically have a look. If the pressure here rises, we can load this surface by the negative pressure, like this one. And the process is stopped. Have a look. Yes? So, moreover, we can measure the force that we need to apply to stop the process. And this force, recalculated to this square, is exactly equal to the pressure from inside. Actually, we can calculate this pressure that is delivered by the small particles, and this is the osmotic pressure. So this process will be interrupted because this level is fixed. No motion possible from right to left. Now, the medical application. This is our patient arm. And for instance, some problems, some abscesses here, inflammation. This means that this area is saturated with liquid, with pus, and the main component of pus is water. However, the concentration of salt is very close to 0 in this area, so we don't have salt, very, very small concentration. What can be done? We can use the solution with high concentration of salt, hypertonic solution, to promote the water molecules to go through the membrane, means skin is a membrane, to go through the membrane to this solution. And we actually pump out by this way pus liquid from the patient. Is the idea clear? Vai tas ir skaidrs?
Jā.
If it is clear, now the more practical question, we are boiling meat. When is the best time to mix salt? At the beginning of boiling or at the end of boiling? How do you think? So,
At the end.
why?
Nu, tad, ja sāla piebērs sākumā, tad gaļa paliktu baigi sausa, ne?
Kāpēc?
Tāpēc, ka ūdens aiziet uz vidi, kurā ir lielāka koncentrācija.
So, if you want to get the dried meat, get the salt at the beginning. Water will leave meat to the salty outside water. And meat will become dry. If you don't have the dried meat, add the salt at the end of the boiling process. In this case, water doesn't have enough time to leave this piece of meat and to go to the outside water. So we have already some knowledge about diffusion, Kinnock's processes, electrical transportation, diffusion and electrical transportation, and osmotic processes. We don't need any engines for these processes. The processes are going themselves. So, and the driving force is a gradient of the concentration from the higher concentration to the lower concentration, or from the higher electrical potential to the lower electrical potential. So this transportation is named as a passive transport or passive transportation because we don't need any engine for this. However, the human organism needs transportation against the gradient from lower to higher concentration, from lower to higher electrical potential. In this case, we need some engine to do this. This is the active transportation from the lower to the higher. To activate this engine, we need some energy, and the energy is delivered because of the ATP molecular dissociation in water. We know this. This is the main energy source for our life. We have spoken about this at the beginning of our course. So have a look. This is a membrane, and this is some protein molecule that is able to provide transportation from outside to inside. This is so-called the gate molecule. For instance, there is some ion. The ion comes close to this molecule, and because of the interaction in between the ion and the molecule, perhaps piezo effect, or maybe some electrical interaction. So there are different approaches to understand what is happening here, but we don't know exactly until now what is the right mechanism. But nevertheless, the molecule becomes open. The channel is open for this ion, and ion is transferring into the molecule, and after that, out. For this, definitely we need some energy to control this molecule, to open it, to make transportation of the ion within, and to open it back to get this ion out. One more example, the gate with the protein molecule that rotates. Trapping the molecule or ion, rotates and leave. Again, we need the energy source. So these are the examples of the active transportation or active transport. The questions, please?
Nav jautājumu.
We already spoken about the electrical potentials that are applied to the membrane. However, have a look. Now, this is a membrane that is located in some liquid with some concentration of ions here and here. So definitely the ions deliver some electrical potentials, and we are saying that the ions, each ion has so-called electrochemical potential. Actually, this is the energy that the ion needs to leave the substance or to add the substance. This is the electrochemical potential. We are saying electro because this is the ion, means the charge, and chemical because this ion interacts with the liquid by electrical or chemical or maybe both ways. So now if the ions are different, if the liquids are different, the electrochemical potentials, please switch off your microphone. Switch off the mic, please. So the electrochemical potentials of the ions from the left and from the right must be different. So, and this is the scale of the electrochemical potential. And so, for instance, on the left side, we have this one potential, and on the right, this one. This is just an example that can be happen. Definitely, these potentials might be equalized. So now we need to draw the line here through the membrane. And you see that the membrane is under the electrical potential difference. So this one minus this one. The membrane is located within the electrical field. And so this is the electrical potential difference that works on the membrane. Is this clear? Vai tas ir skaidrs?
Yeah.
So again, if you have the liquid here, here, and here different, means immediately the membrane is under the electrical potential difference or under the electrical field. Now let us go to consider the axon. So this is the morphology of the axon, like the cable that connects to the dendrite and to the terminals. So we are getting the signal from this one, go through this cable, from the dendrite, go to through the cable and to the brains. So if we go to the cross section of the axon, we see the membrane of the axon. So this is the thickness of the membrane, and two different liquids. This is the internal liquid and this is the external liquid. So definitely they are different. In generally, both liquids are electrically neutral. However, the ions here are different. And because of the electrical field that works on the membrane, we have in reality such a distribution of the ions. The negative ions from internal liquid are located here, and definitely from the external, the positively charged are located here. As a result, we have the electrical potential difference on the membrane. So have a look, the natrium ions outside, the calcium ions inside, and the negatively charged particles, maybe ions or maybe electrons, are here. So now, if you go to measure the electrical potential difference at the membrane, we meet the difference approximately 70 millivolts. It's a measurable value, and we know this more or less exactly. So now we have calcium, potassium inside, with the covalent radius 203 pm, picometers. And we have the natrium from outside with the less covalent radius, 166 picometers. Definitely, this natrium ion has a chance to go through the membrane into the internal liquid. And just because of some fluctuation, maybe because of some electrical excitation, because of some reason. We are saying the activation reason. So it's in. What next? Because of the electrical interaction between these positive and these positive ions, these ions must be redistributed. The potassium ions must be redistributed. Actually, we have the electrical signal that passes through the axon. This electrical signal is very sharp because this process goes very, very fast. We have very sharp electrical signal that passes through the axon following the soliton mechanism. I believe that you You remember the soliton mechanism that we have spoken somewhere in the mid of our course. Just please remind the domino effect. So, at this place, instead of this natrium atom, we have the induced negative charge. Because of this negative charge, should be neutralized, and this potassium ion concentration is some extra concentration that actually isn't thermodynamically isn't equilibrium concentration. So that is why some extra potassium ion is able to go out, and it has happened. After some time, everything is relaxing back. So we need excitation, we're saying activation of the axon by some way, and we, as a result, we have the electrical pulse that goes through the axon, giving the signal. So now have a look what can be happen. So at the beginning we have minus 70 millivolt in the membrane. Now we have activation. As a result, the potential rises to roughly plus 40 millivolts. And when the activation is interrupted, so the potassium ion comes back. So this time interval is very short, a couple of milliseconds. And after that, we have the relaxation. So after that, again, some milliseconds, the signal relaxes. And in reality, so this is a for experiment, minus 70, excitation, activation, repolarization or relaxation, and some process to stabilize, not falling down by this way, but falls down like this one to stabilize. So this is very briefly about the axon activations because of the electrical field. So some questions, please. Vai viss ir skaidrs jums?
Šajā gadījumā aktīvais transports ir tikai tāpēc, ka vajag to pozitīvo nātrija lādiņu dabūt jau pozitīvā vidē. Tā es saprotu.
Jā, un tam ir vajadzīga šī aktivācija. Kāda veida viņa notiek, tas ir ārpus mūsu kursa, tā ir jau sākats biofizikā, un jums būs tā biofizikas, tāda introduction jums notiks. Es arī par to jums arī stāstīju. Kādi tur varētu būt mehānismi. Tam vēl jautājumi? More questions?
Ir skaidrs.
Okay. Tagad jums sāksies in 4 minutes. You have the test. I'll stay somewhere 5-10 minutes online. If you have some problems, you can ask me. And about the next lesson, the next class will become the last one. And we have again the test that will cover the topics behind optics. So everything behind optics, we have the test. Next time. We finish the theoretical part. I need somewhere 30-40 minutes to finish, and after that we have the test. So now please open Ortus and tell to me if you see the test.
Jā, ir redzams.